Hi, good morning. So here we are going to start the first order differential equation video problems. And so let's start with number 1. So number 1 is this problem that's y prime equals x squared minus 4, 3y plus 2. And so looking at this, I can tell that this is going to be a separable equation. So we can solve this as one, and that's going to be of the formula dy dx equals f d of y. And so we see that that's kind of what we have here. And so what I do is I expand the y prime to dy dx equals to x squared minus 4, 3y plus 2. I'm going to divide out the 3y plus 2 on both sides. And then I can just rewrite that as 1 over 3y plus 2 dy dx is equal to x squared minus 4. Put that in parentheses. And then here I'm going to multiply out the dx. So I'm left with 1 over 3y plus 2 dy equals x squared minus 4 dx. And so now we can take the integrals of these. So it's going to be 1 over 3y plus 2 dy. And that's going to be equal to the integral of x squared minus 4 dx. All right. And so for the left-hand side, we're going to have to use u substitution to make it a little less complicated. And so we can set our u equal to 3y plus 2. Our du is going to be the derivative of that, so it's just going to be 3 dx. Divide out the 3, du 3 equals dx. And so we can now rewrite that. So it's going to be 1 over u, and then du over 3. We can pull that out. And then we have 1/3, 1 over u du. Right? And so now we can just rewrite that as, we can take the integral of 1 over u, which is just going to be the natural log of u. So that's going to be 1/3 natural log of u plus c, which is just the constant variable. Right? And then now we can just substitute back the u. So that's going to be 1/3 ln 3y plus 2 plus c. And I'll write c of 1 because we're going to have a c on the other side as well. And then the integral of this, we're going to have x cubed over 3 minus 4x plus c, and I'll write 2. That's going to be that here. All right, and so now we're going to try solving for y. So the first thing I'm going to do is I'm going to multiply out that 1/3. I'm going to multiply by 3 so I can get rid of it. And then we're going to multiply 3 by the other side as well. And then we can see here that 3's are going to cancel out. And now we can just kind of rewrite this. So it's going to be ln 3y plus 2 plus c1 equals x cubed minus 12x plus c2. And then for the next part, I'm going to get rid of the natural log, and I'm also just going to condense the constant on the right-hand side so we don't have two of them, so it doesn't get confusing. And so I'm going to multiply by e in exponential e. And so now we're going to have, well, these are going to cancel out. And so now we're going to have 3y plus 2 equals e x cubed minus 12x plus c. And then we can bring the c out in front of the exponential. And I'm just going to rewrite that really quick as 3y plus 2 equals c times e to the x cubed minus 12x. Right. And so now I'm going to subtract by 2 on both sides. And so now I'm going to have 3y equals ce cubed minus 12x minus 2. And then final step, just divide by the 3 to get y by itself. And so we get y equals ce x3 minus 12x minus 2. And now we're just over 3. So this is going to be our answer, our general solution. Because we didn't have any points or any, like, it wasn't an initial value problem, it's not going to be like our particular solution, but just like a general solution. So yeah, there's the first one. Okay, moving on to number 2 now. We have the problem y prime plus 4y equals e to the x. And so based off the format of this, we can say that this is going to be a linear equation, as it has the format dy dx plus p of xy equals qx. And so first thing I'm going to do, oh, and then we also have the initial values of y of 0 equals 4/3, so essentially 0 4/3. So first I'm going to write out what my p of x is. That is going to be 4. And then I'm going to write my q of x, which is going to be e to the x. And then to find the integrating factor, I'm going to write that as I of x. That's going to be equal to the exponential of the integral of p of x dx. And so we can fill those numbers in, and it's going to be 4 dx. And so that is just going to give us e to the 4x. All right, so now that we have that, we can write that as using the formula here of y equals 1 over ix multiplied by the integral of the integrating factor, q of x dx. So now that we have that, we can write 1 over e to the 4x times the integral of e to the 4x multiplied by e to the x dx. And so because these are like terms and they're being multiplied together, what we can do is that we can add them together. And so now we are left with y equals 1 over e4 to the x integral of e5x dx. And so now we can go ahead and solve for this integral. Again, we're going to have to use u substitution just to make it a little bit neater. So my u is going to be that 5x. The du is going to be 5 dx. And then I'm going to divide out the 5. And so I'm left with du5, I don't have to rewrite it, du5 dx. Oh, I'll rewrite it. Okay. And so now I'm going to go ahead and rewrite that over here. So that's going to be EU du over 5, pull out the 1/5, left 1/5, EU du, and then the integral of this is just going to be 1/5 EU plus C. And so now we just substitute back the U, and so it's going to be 1/5 E 5 to the X plus C. Okay. So now we can multiply these together, and since e to the 4x is on the denominator, when we multiply that to e5x, that's just going to reduce down to 1x. And then that's going to be c over e to the 4x. So we're going to have 1/5 e to the x plus c over e4x. And so that's going to be our y equals. And now we can go back and see that we have the initial value, and we can solve for c. All right, so now if we plug in those numbers, that's going to be 4/3 equals 1/5 e to the 0 plus c over e4 to the 0. And so e to the 0 is just going to equal 1, so we're just going to have 1/5 plus c over 1 equals 4/3. And so now we subtract out the 1/5. Let's see, 4/3 minus 1/5. Find the common denominator, it's going to be 15. So we just do that. So that's going to be 20/15 minus 3/15. That's going to give us 17/15. Right, so let's see. Yeah, so 17/15 equals c over 1 times the 1, doesn't change. So our c is going to be equal to 17/15. Right. And to save some space, I'm just going to rewrite everything over here. So now that we have our c, we can rewrite our original general solution that we got over here. So that's going to be y is equal to 1/5 dx plus, and to make it a little bit more legible, I'm going to write 17/15 and then e to the negative 4x, because it was on the denominator, so we just wanted to note that. All right. And put that in, I'm going to go ahead and put that in parentheses now. All right, so that is our answer. This is our particular solution for this linear equation. Yeah. Okay, for number 3, we have the equation 3x squared minus 2y squared dx plus 1 minus 4xy dy equals 0. And so based off this, we can tell that this is going to be an exact equation, as it has the form m dx plus n dy equals 0. And so this is going to be our m, and this is going to be our n. All right, so the first thing I'm going to do is I'm going to check for exactness. So that's going to be taking the partial derivative. That's going to be m with respect to y. So that's going to, if we find the derivative of m with respect to y, we see that we have negative 4y. if we find the derivative of n with respect to x, we see that we have negative y. And yeah, so these actually are exact. So our my is equal to our nx. So that means that they are exact. So now what we can do is we can integrate either the m or the n. I'm going to go ahead and choose the m. It seems like the easier option to integrate. So let's do that. So f of x equals the integral of 3x squared minus 2y squared dx. And that is going to give us 3x cubed over 3 minus 2xy squared plus g of y. And this g of y is going to be the function lost along the way that we have to look for. And of course, plus c, the constant. And we can rewrite this to simplify that as just x cubed minus 2xy squared plus g of y c. So now we have to look for that g of y. And how we look for that g of y is first we are going to take the partial derivative of f with respect to y. And so that's going to be our function here. And so if we take it with respect to y, we see that we get negative 4xy plus g prime y. And so now that we have that, we can set this, what we got, equal to the n, our n that we had here in the beginning. So that's going to be 1 minus 4xy. So 1 minus 4xy. And so we already see that we can get rid of these two, and they're going to cancel out. And so we are just left with g of y equals 1. And of course, we have to integrate these. So we're going to get g of y, is equal to the integral of 1, and that's going to be dy. So we're going to end up with g of y is equal to y. So now we can rewrite our original function, and that is going to be f of xy is equal to, let's see, x cubed minus 2xy squared plus y plus c. And that is going to be the solution of this exact equation. It was very convenient that they were exact and we didn't have to find any integrating factor. And yeah. To our last one. Oh, number 4. We are given y prime is equal to x minus 1 over y. And we're also given the initial condition y3 equals 0. And so we are given the prompt of, is there a solution to this equation? And is it unique? All right. And then if we're looking at the form of this equation, we can see that it is in the separable form. So it's going to be a separable equation. So yeah, first answering the question of, is there a solution? There is a fraction in this equation. And then we also see that y is equal to 0 and y is on the denominator. So that would make this equation look like that. So that would mean that this would be undefined, since y is on the denominator and it is equal to 0. And so we answer the question, when does this equal 0? And that's going to be when y equals 0. And in this case, y does equal 0. All right, and so since the initial value problem states that y equals 0, then this function would be undefined since it has a 0 on the denominator. And so if it's undefined, then that means that there does not exist a solution around the points of the ones we were given, which is 3, 0. So yeah, there does not exist a solution. It is not continuous around the points 3, 0. So now we move on to the question of, is it unique? And so for this, we can look for this based off of using partial derivatives with respect to y and also using the quotient rule. And so how we use the quotient rule, that is going to be, if we have fx, g of x, and that's going to be equal to g of x, f prime x minus f of x, g prime x over g of x cubed. I wrote this parentheses wrong. G of x cubed. And so if we take the partial derivatives, we have, with respect to y, we have y, and that's going to be 1. And then we have x minus 1. Because there's no y, it's just going to be 0. And now if we rewrite that, we have y 0 minus x minus 1, 1, all over y squared. And so we see already we're kind of in the same situation where if we plug in the initial value problem, y is equal to 0, and it's going to be undefined. So because there exists no solution, because this function is not continuous around the points that we were given, we can say that there does not exist a unique solution. Unique solution to this function problem. And then we can use Picard's theorem to confirm that there is no unique solution. So yeah, hopefully I did this one right, that there is no solution because it's undefined. And then also we use the quotient rule here for uniqueness to see if it would give us an answer, but yet we end up with another undefined function. So there is also no uniqueness. I'm just going to go ahead and highlight these. There does not exist a unique solution, and then a solution does not exist along those points. All right, and that's number 4.